Okay, so welcome to the afternoon session. This one is on separation logic, and very soon Alejandro should start explaining us about error credits. Yes. Yeah. I'm just waiting. That's fine. Yeah. No, okay. So. Okay, you can, okay. Does it show up? Okay. Good.
Should I just start? Okay. Thanks everyone. This is joint work with Philipp, Markus, Haley, Simon, Joe, and Lars, most of which are in the room now. Okay, let me motivate it with this following example. Suppose I execute 2 queries on a hash function, and then I check that the result I get is different. What kind of specification would I want to write for this program? Well, arguably, I would want to say that if the keys that I'm querying are different, then the result of this comparison should be true. But this is not entirely accurate, because there's a small probability that there will be a collision. And in previous work, this has been solved by annotating the Horde triples with an error probability. And then, well, the way this can be composed is by adding the probabilities in the sequence rule. And this works mostly fine, but it has some limitations. So the first limitation is that there's no way to make the error for C2 depend on the state after C1. The epsilon2 is completely uniform. And secondly, I would argue that this is not very modular in the sense that it's complicated to build clients of these specifications. And I will argue why this is the case a bit later in the talk. OK, so what do? Our idea is that we present a new logic that we call ERIS, which is a higher-order separation logic to reason about the probability of errors in higher-order probabilistic programs. And the key to our approach is that we will introduce a new representation predicate that we represent with this line in epsilon, which means that you own epsilon error credits. And the idea is that epsilon error credits will allow you to pay for an operation that might fail with probability at most epsilon. And since this is a standard separation logic resource, then you get compositionality and modularity from your ambient logic. And in addition, this also enables new reasoning principles that were not possible in previous work. And everything that I will present today has been fully mechanized using Coq and Iris. OK, so let me say a bit more about how this works. So as I said, you first start by adding a new predicate, line in epsilon, which asserts ownership of epsilon error credits, where epsilon is a real between 0 and 1. This on its own has no meaning. It's just an abstract predicate. And there's nothing probabilistic to it. It only gets probabilistic meaning through Horde triple. So in particular, if you prove a Horde triple with epsilon error credits in the precondition and phi in the postcondition, this means that this program will, with probability at least 1 minus epsilon, either diverge or return a result that satisfies phi. Here, divergence is a valid behavior because this is a partial correctness logic. And it's important to remark that here phi is, again, a standard separation logic assertion. There's nothing probabilistic to it. And in fact, if you make epsilon be 0, then this is just your standard deterministic partial correctness. OK, now we need to add some new laws that the error credits will obey. The first one is that you can always obtain 0 error credits out of thin air. You can either join or split error credits if you own the sum of them. And if you own one full error credit, then you can just prove false. The intuition of this is that if you're trying to bound a probability of error, and this is at least 1, then any behavior is valid. And the final and key property of error credits is that they can be distributed along probabilistic choices. So suppose I own epsilon prime error credits, and I flip a coin. Then I can distribute the error credits across the outcomes. I can assign some amount of error credits to false and some amount of error credits to true, as long as the average is what I had at the start. In this way, you can make the error credits that each outcome gets depending on the actual outcome, instead of uniform as in previous work. And in the same manner as you can do it for a flip, you can also do it for choosing randomly between n+1 outcomes. And this slide is the takeaway message, because this is basically all there is to it. If you have your standard iris deterministic logic, and you add this, then it suddenly becomes a probabilistic logic. If you have proven anything in your iris development for a deterministic sequential program, then it's still true. And you only need to use error credits whenever you want to do some sampling instructions. And everything else that I will present in this talk is just a consequence of these laws. OK, so let me show some of these consequences. So one useful way to think about error credits that is it's not as general, but it's useful in proofs, is that if you own epsilon error credits, you can use them to avoid a set of bad outcomes whose probability is at most epsilon. This is represented by this rule. Here, x is just some set of outcomes that you want to avoid. And if you own an amount of error credits that is equal to the probability of this set, then you can just ensure that you will sample outside of this set. And the intuition of why this is true is that, well, you can just distribute your error credits, and you will assign 0 to the good outcomes and 1 to the bad outcome. And then whenever you get 1, then you can just immediately reject this branch. OK, let's see how this can be used in practice. So let me go back to my example with the hash function. It's often very useful to represent your hash functions as a lazily sample partial function. So this means that we will have a partial map from keys to values. And then whenever we query the hash function, we will look in the map. If this has been sampled before, then we just return whatever is that was sampled before. Otherwise, we need to sample it fresh. So you will sample a fresh value for this key out of all the possible set of outcomes. We will store it on our partial map and return it. And then the next time, we will get the same thing. So what kind of specification we want to write for this hash map? Or sorry, hash table. Well, let me propose this. So first, I say that if there's no collisions in the hash function, meaning that no two keys point to the same value, and I query the hash function with an element that is not in its domain, and I own this amount of error credits that depends on the size of the current domain, then what I will get is a hash function that's still collision-free. And the idea how this works is fairly simple. So first, when I look up the partial map, I know that since it's not in the domain, I will go to the non branch. And here, I will sample a fresh value for this key. And since I own an amount of error credits that is proportional to the, well, it's exactly the probability of sampling something in the domain, meaning something a collision, then I will just use the this amount of error credits to ensure that I sample something that is fresh. And then I will store it. And then what I will get after this will be collision-free. OK, so it's fine. But but there's a problem with this specification, which is that if a client of this data structure wants to use this specification, then this client needs to track at every point what the current size of the domain is. And this is not very practical because this will crop up everything everywhere in the proofs, and clients of this client will also need to track the size of this hash function that they cannot even see, and this is not very modular. So we can do something better. Suppose the client is going to execute a sequence of m insertions, and I know that this is a hard upper bound. Then the error that I need to spend looks a bit like this. First, I can just use 0 error credits, because there's nothing in the domain, so there's no way to get a collision. Then I will use 1 over 2 to the s, and so on, until the last insertion that will consume m minus 1 over 2 to the s. So the key idea here is that we can prove a more modular specification that tracks the amortized error. What does this mean? Well, instead of using the amount of error credits that is dependent on the current size, I will just use some constant e that I will use for every single insertion, and I will ensure that the sum of all these e's is equal to the sum of all the actual errors that I will consume. And this, of course, some of these operations will need more error credits than they will be given. Because, for instance, the ones towards the end, E is not enough to pay for the actual error that you're incurring. But managing these error credits, it's basically achieved through standard separation techniques. OK, let me say a bit more about how this is done. So I can prove a new specification that uses another representation predicate for the collision freeness that I call call-free am for collision-free amortized. But if you see the rest of the precondition is essentially the same. I ensure that n is not in the domain, and I will get an amount of error credits that is uniform, is constant, as opposed to dependent on the current size of the hash function. And then the representation predicate will basically carry out the error arithmetic for me. So first, the representation predicate will contain a reserve of error credits. It will contain a condition on this amount of error credits that essentially states that the current reserve plus what I will get in the future insertions is enough to pay for all the actual error that I will be incurring. And I have also the old representation predicate that just says that there's no collisions within the hash function. But not only I can reduce the old representation predicate to build a new amortized representation predicate, I can actually derive it from the old one. So the idea of how this proof is going to work is that you can open the representation predicate for the amortized cost. You will get some reserve of error credits. You will get your old collision-free representation predicate, and then you will insert something in the hash map in a collision-free manner. You will consume some amount of error credits. You will get back some excess, and you will put it back in the representation predicate and then close it. And then basically the second condition will ensure that this will always be possible. There's more on the paper that I will not be able to cover for this talk. So we verify some clients of the hash function. In particular, we verify some resizable hash maps that use the hash function as a client. And the idea here is that there's no maximum number of insertions. You can actually resize, and then you have some uniform amount of error credits for as many insertions as you want. We also verify some Merkle trees that use the hash function as a client. And in addition, we also present a total version of a total correctness version of the logic, meaning that we consider divergence to be an error behavior. And this means that, in particular, we can use the logic to reason about almost sure termination, which is termination with probability 1. And here, the key idea is that we introduce this new principle that we call error induction. And we'll present it very briefly. If you've seen Levi induction, it looks quite similar. So basically, the idea is that if you're trying to prove P, which is an arbitrary separation logic predicate, and you own epsilon error credits, then you can instead prove the goal on top of the rule. And then here, the key idea is that you're going to get an induction hypothesis that looks like this, meaning that you need to pay an amount of error credits to open it. That is, it has been amplified from the original amount of error credits that you have. And well, the key idea, or the intuition of why this should be true is that if you are able to amplify your error credits by some k that is larger than 1, then you can do it as many times as you want, and eventually get one full error credit, and then you can prove false, and then anything follows. Besides this, we also do other case studies in the total version of the logic. We verify termination of some large family of rejection samplers, and we analyze a randomized SAT solver that does a random walk through the possible state of solutions until it finds one. And we show that it's correct and that it terminates. Besides this, we also discuss the semantics of this language and why this is sound. OK, and with this, I would like to just conclude. In this work, we have introduced ARIS, which is a logic version about the probability of errors in probabilistic programs, and that is basically enabled by representing the error credits as a separation logic resource. And if you want to see more details, you can look at the paper, you can look at the code, you can email me any questions that you have. And I will also use this opportunity to say that Aarhus University is hiring both PhD students and postdocs. So if you like this kind of work, you can write to Lars, or you can just talk to us in the break. Thanks.
So, we have time for questions. Oh.
Thanks for the talk. Two questions that are somehow related. So as you know, the previous work was inspired by the union bound,
yes.
Which is a way to compose this error bound. And there are some other work on using separation logic for independence of random variables. So a natural question is, are you able to represent a different composition of error bound, like Chernoff bound, for example, using this logic?
I don't think you can. So here, this logic is not. So the separating star does not represent independence. It's just your standard separation logic.
The error splitting, basically, the star. And so you cannot use it at the same time for independence.
I don't think so. It would be interesting to see if there's a way to adapt this to this other approach, but not on the current state,
Hey, thanks for the talk. Quick question regarding the soundness or adequacy. Could you comment on how difficult is it to prove it, and in particular, how complex the base semantics of the target language is?
So the base semantics is like a small step operational semantics for a higher-order language. So you have it's probabilistic, right? So it's a map from configurations to distributions over configurations. The way that semantic proof works is that basically you, well, if you've ever seen the IRIS weakest precognition, then it's defined by guarded recursion on the execution of the program. And then every time you take one step in the program, then you can track the errors, and then you can distribute them through the possible outcomes. And then it's based on this notion of graded lifting of propositions. So internally, the weakest precondition is whenever you take a step, then what is inside the say inside the later of the weakest precondition is going to be like a lifted predicate. We can discuss it offline if you want. But
thanks.
So IRIS, like you said, uses guarded recursion. So traditionally, proving anything about total correctness has been very difficult.
Yes.
Like how were you able to do this?
So, but you can just define total